So I'm here to talk about the Volta architecture in a clustered HA configuration, as opposed to Volta being run as a single instance by itself. So the abstract you've already seen, I'm not going to dwell on it, though we won't work through several example API calls because the presentation's already too long without them. So I'll talk a little bit about them, but we're not going to go through them in any kind of detail. Otherwise, we're going to time out. So this is the high-level diagram of a Volta deployment. Oh, now I'm echoing. So here we have the focus of this talk is going to be on Volta proper, the entire stack itself. We're not going to be talking too much about ONOS. So the Volta stack basically has a load balancing proxy. It has the core of Volta, which is the vCore cluster, and then a bunch of services that are required by Volta to run. So console, FluentD, Kafka, and a registry. And then you have Docker running in swarm mode, and finally the hardware. So 2N+1 hardware platforms, or bare metal platforms, or VMs. It can be either or. And the PON network is over here through talking to Volta through the device adapters. So I'm going to go through each of these guys in order. You'll notice the OHF agent is sort of weird here. It's bound service up at the top, and it's sitting over here, and I'll explain that in a little bit. If you have any questions, feel free to interrupt, but it's probably a good idea to wait to the end, because otherwise I may not reach the end. So the high-level concepts are Docker is used in swarm mode. There are 3 overlay networks used to support Volta. There's Volta Net, there's Kafka Net, and there's Console Net. And we'll see why we have them. They each serve a purpose. Each service today is individually started through individual compose files. So Kafka, Console, FluentD, they're all started with separate compose files. There are good reasons for starting some of them in a specific order. You don't necessarily have to start them all. You could combine that, but we haven't done that yet. Okay. All services are running in load balance clusters, and the number of VMs, as I said earlier, or servers is 2N+1. And an important note: the current implementation is more of a fast failover. It's not millisecond HA that's coming. We have a change in the architecture that will get us to milliseconds failovers. Right now, it can take 15 to 30 seconds, depending on the total number of devices being managed in the cluster, for a core to come back. And you'll see why that's important. Depending on what you're asking the system to do, you may take a hit during that time. So let's start with a proxy. So the Envoi Proxy is a C++ implementation. It was built by Lyft. It's called Envoi, and it's available from the website that's published there. I'm sure when you get the charts, you can go look at it. The reason that Envoi was chosen is twofold. One, it supports hitless reconfiguration, which means that you can change its configuration and it will actually seamlessly load the new configuration. It won't drop any connections. It'll hand them off. It does a very good job. It also supports HTTP2, front end, back end, which is important for gRPC. And finally, it supports HTTP front end as well. And it will take the compiled files from gRPC, and it will actually present a REST interface northbound. So you can actually get an HTTPS northbound interface directly by using the protobuf definitions. Finally, to run as a single instance today, Swarm will restart it if it dies. It's pretty robust. I haven't seen it die yet, but we do need a solution to make sure that when we claim we have millisecond switchover, that it can actually, there's a second proxy waiting in the background to take over the role. And the reason we have to run it as a single instance is because it maintains 2 Roundrobin queues, as we'll see later. And finally, the proxy connects to only Volta Net as the network. So what it does, it will watch a specific key. When it comes up, it's going to watch a specific key inside the console cluster, and it uses the values in that key to configure itself. There's a special daemon called Envoi D that starts the proxy. It monitors console constantly, and it reads the value of this key, and this key contains all the IP addresses of all the instances of the Volta containers that are running. So if that key changes, Envoi D will restart console. So what happens? Let's assume that Envoi's been running for a while. Suddenly there's say an instance of Volta that crashes, which doesn't happen very often, but let's say it does. There's an instance of Volta that crashes. There will be a notification to Envoi D that the console key named assignment has changed. So what it'll do is it'll look at the new key and find out, oh, there's only 2 Voltas. Okay, so it will then load a configuration template, which is a configuration template, a Golang template, which is very much like Jinja templating. And it will take the values that it got from the key and generate a new config and write it to the disk. And then it will start a second envoy. The second envoy will realize that a first envoy is running. It'll ask it to take over all the sockets that it was handling. The first envoy will drain all its connections and gracefully die, and there will be no hit because the connections were handed off seamlessly. Down there are the names of the different config files, depending on the options you've given the proxy. So as I said earlier, there's two round-robin queue, the 2 round-robin sequences that are maintained by the proxy. One is maintained for create devices. This is done for load balancing. When you create a device in Volta, the create device call, or the enable call, if you're using the CLI, will create a device on one core, and then the next, and the next, and the next, and it maintains that round-robin sequence independently of another round-robin sequence that gets called for every other request. So what that means is that other requests won't interfere with the sequencing that the round-robin sequence is using for device creation, which means that when you create your devices, they'll be evenly spread across all the different Volta cores. And I've tested this up to 1,500 OLTs, a total of 3,000 devices when you consider the ONUs, and the spread is very, very good. The proxy is actually pretty smart because if one core starts getting overloaded, it'll skip it in one round-robin sequence, and then it'll give it 2 in the next one if it realizes that there's an issue. Sorry, there's an issue. Let me just get some water. The OF agent. The next one I want to talk about is the OF agent, and the reason I want to talk about it, even though it's a northbound service, it's not behaving like a normal northbound service. So it doesn't connect to vCore through the proxy. It connects directly to the Volta Core, and there are reasons for that. So ONOS requires each logical device to maintain one distinct connection with it, just like any OpenFlow device. So the OF agent maintains a connection between ONOS and the vCore handling the logical device. As you saw earlier, I said the proxy is actually doing a round robin. So the devices are spread across all the vCores. So what the OF agent does is it will maintain a nailed up connection to the core that's managing the device, and then a nailed up connection to ONOS for the OpenFlow packets to flow. So in terms of, well, okay, so I said all that. And finally, it connects only to VoltaNet. So how does the OF agent start up, and how is each one connecting to a different one? So what happens is that each agent will try and connect to a Volta core. If that core already has an agent connected to it, it'll just reject the attempt. And leveraging the fact that that overlay networks in Docker Swarm will return IP addresses in a round-robin sequence for each different member participating in that network or participating in that domain. Eventually, each one of these OF agents will hit on a core that's not actually using or doesn't have an OF agent associated with it, and it will bind correctly. So the same thing happens when an OF agent comes down. Okay, the Volta core will realize that the agents come down because there's no more heartbeat. So it will basically say, oh, I'm ready to accept another OF agent connecting to me, and then as the Docker swarm restarts a new version of that agent, it will attempt to connect to the cores as usual. It'll be rejected by 2 and finally connect to the available one. So same if a Volta instance goes down. So here in the example, what we have is, for example, OF agent 1 gets the IP address 10.1.1.10, attempts a connection. That Volta Core didn't have anything connected to it. It works fine. The second OF agent attempts to connect to the same one, because when it requests the address of vCore, it gets 10.1.1.10 because other things have been making requests, so the round robin sequence happened to land on the same core. It gets rejected, it fails. It tries again, and I'm going to make this very short. It succeeds. And then this one, lo and behold, just tries and gets the IP address of the third core. And then you relationship between the cores and the OF agents. This is the only exception that doesn't go through the proxy. Okay, the next one is the Volta Core. This is by far the most complex part of the entire system. So the Volta Core, the cord/Volta container runs in a cluster. It's known as vCore, if you've ever seen a HA deployment. And there are 3 critical functions that are used to support HA. There's a dispatcher, a coordinator, and there's persistence. So any of you who have worked on Volta before knew that there was a global service and a local service. The local service is no longer used. There is a gRPC API that presents only the global service now. And all the global requests, except create device, as we saw earlier, are processed by the dispatcher first. So we saw this earlier, right? The create requests will be handled by the proxy. They'll go straight to a specific core. So if a core receives a request that's for a device that's local to it, it will just forward that. It will forward that request directly within that core and provide the reply. If a request is for a device that's being managed by another core, and the dispatcher knows this because it has access to console and it knows which devices are managed by what core, it'll forward the request onto that core and then send the reply back. And finally, if a global request for a list is asked, for example, list devices, that's a request that requires information from all cores. It'll be broadcast to all cores. The core that received the request will basically aggregate all that and provide the response back up. So I explained all this. So finally, persistence. So persistence is handled through. Let's go to the coordinator. So the coordinator does leadership election. I quoted this because it's not the leadership election algorithms you're used to. It's sort of a race. Whoever locks the console key first gets elected the leader, and then the other guys are out of luck. If the leader dies, all the others are notified that the key has become free, just the same way as the proxy is notified about a key change for a different key. Then they race. The remaining 2 Volta cores will race to try and lock that key, and whichever one gets it first becomes a leader. Okay, that's the leader election process. The coordinator also manages the list of vCore members, and it creates that key that the proxy monitors. So that key that has the assignment information is the one that the proxy monitors, and the coordinator creates and manages that key. And it assigns new work instances. So basically, if a core dies and comes up, the coordinator will tell it, okay, you're vCore 3, because 1 and 2 are still alive, so you get the work that vCore 3 was doing, and it will go to console and pull the work up. If we decide to scale Volta, this isn't fully implemented yet, but if you scale the number of cores, then what the coordinator will do is it will shed some work off the current existing cores and hand them to the new core that was just created in the scaling exercise. And finally, persistence is through console. It's used by the coordinator. It stores the data model for Volta, and it's a convenient point to do a backup and restore of your entire running configuration because all the data for all the devices is stored in console and persisted on disk. And Volta only connects to the VoltaNet network. So as I said, it's the most complicated of all the services. So here are the interactions. So the Volta Core issues KPIs and events through Kafka. Persistence is handled through console, as discussed earlier. The coordinator has one key that it uses for mastership election. Logging is done through FluentD. Now here's the gRPC service. So Envoi makes all its requests to Volta through the gRPC service. If a create is received, it doesn't go through the dispatcher. It just goes straight to the core itself. The OHF agent goes straight through to the core. Everything else goes through the dispatcher. And if the dispatcher realizes it's local, it sends it here. Otherwise, it sends it to the corresponding core. And the coordinator is communicating with all the other active Volta cores. And each one of these guys looks exactly like this one here. Okay, and then you've got the adapters that speak southbound. Kafka and Zookeeper. So Kafka is the KPI, is the mechanism for distributing KPIs and events to upstream systems. Okay, so there's a special overlay network that's created for Zookeeper. And that network is used for the Zookeepers to find each other and for Kafka to find the Zookeepers. Okay, Zookeeper is a key value store that's used by Kafka. If we could have gotten away with using console for both, we would have. We can't because Kafka uses Zookeeper, and in a future release, I believe they're getting rid of Zookeeper altogether, and they won't need it. And by the way, the future of Volta is probably etcd, not console, because console's been very, very flaky. It took a lot of option twiddling to get it to work. And Kafka needs to know about all the Zookeeper instances. So the Zookeeper's domain names are used to locate them. If you look at the compose files, you'll see that they're referred to by name. And Kafka connects to both Kafka Net and Volta Net, obviously. So here's the way it looks when it's deployed. There's Kafka Net. So Kafka and Zookeeper on Kafka Net. So Kafka can find its Zookeepers, and the Zookeepers can find each other. And then there's Volta Net. So this amoeba over here is Volta Net, and the three primary users of Kafka are shown here. There's a lot more processes in there, but those are the three primary users of Kafka. Okay, console. So console, as I said earlier, is a primary key value store for Volta and Flaky. Console's deployed in global mode. It's the only application that's deployed this way. So typically, you'll deploy applications with replicas equals some number, which means that if a server dies, a new instance of that container will be started on one of the surviving servers. With console, this is not the case. With console, if one dies, the other two continue to operate until that one comes back. Attempts to do anything other than that will wreak havoc. So that was one of the tweaks that we needed to make sure that it worked. Specifically because we need to persist the data to disk, and if a second console were started on the same machine as another console, they both target the same directory or the same path on the file system and overwrite each other's data, and there's hell to pay for that. ConsoleNet is used for the instances of console to discover each other, and we had to play games here too. So we had to basically give it an IP address space of 5 addresses or something ridiculously low, and this allows us to exhaustively list all IP addresses in the subnet on the console command line. So it just keeps retrying each one of those IP addresses until they all find each other. You can use the virtual IP, but that doesn't work well either. And split brain doesn't work. And in our testing, split brain never worked, no matter what way you try to do this. So console connects to both ConsoleNet and VoltaNet. It mounts a file system, as I said. You could use an external SAN if you wanted. And you'll find that console in the old compose files appears everywhere because it used to be used as a DNS service for the initial implementation of Volta. Swarm provides that now, so you can ignore any references to console for all the other components of Volta that are started up. Console interactions, it's fairly simple. Console sits on ConsoleNet, so that all the instances of console can find each other, and then Envoi D and Volta both communicate with console to get information. Oh yes, and there's another one, which is a backup script that communicates with console to pull all the key value information out of console and save it. But that's not a container. Okay, finally, FluentD. FluentD is a logging mechanism. So FluentD is used as both a log intake mechanism and an aggregator. The only container using FluentD today is the Volta Core, but theoretically, as things move forward, we're going to all be using FluentD, at least all the software within Volta that isn't already another, like Kafka, for example, would never use FluentD because it comes from a third party. GlusterFS is used as a replicated file system to store the logs, and currently it's a loop-mounted file within which a file system is created. That's been done for two reasons. One is you don't have to partition your disks in any special way when you're installing Ubuntu, so you can just do a quick click through all the installation, and you end up with a device, which, well, to the system looks like a device. It's a loop device. And the other thing is it limits the size of the logs. So just like a partition would, you basically, if you fill that file, that's it. It won't go rampant and completely fill your disk space, causing Volta to crash horribly. Okay. The replication mode is dispersed for this GlusterFS system. There's another one. That's why I'm calling this out. It's similar to a RAID 5. That is, there are two bricks used for storage, and then one brick is used for parity. So you can lose any one of the three bricks, and you can still get your data. Okay. There are two intakes. There are two FluentD intakes that are running in a cluster, which means that they've got a virtual IP. You can access either or. And then there's one aggregator running, two aggregators running, one in active and one in standby mode. And basically the intakes communicate with the aggregators, and the aggregators themselves, if one dies, the heartbeat will go away, and the FluentD instances know to continue sending information to the remaining aggregator. So this is the interaction. So Volta is sending the logs to this cluster. They're going to either of these two. These two are typically only writing to the primary. And if anything happens, the active one, I mean, if anything happens and the heartbeats stop flowing between these guys, they will immediately switch to the standby aggregator. And these aggregators have the GlusterFS replicated storage mounted. The registry. So the registry is basically a Docker registry. We're running it as an insecure registry. It's implemented on port 5001 on any of the hosts. And this makes it very simple to push new Docker images or pull new Docker images into the system and then deploy them and do rolling upgrades and the like. So it's a single instance. The registry isn't critical. It's not like if you lose the registry for 5 minutes when the cluster is up and running, it's going to cause any issues. The only time it'll cause an issue is if you're trying to upgrade something and the registry isn't there. You just restart it. Docker Swarm will just restart it. The registry, again, uses a GlusterFS replicated file system. It's a loop-mounted file, but it's basically replicated. So it's RAID 1, which means that everything is replicated on every machine. So you can actually lose 2 bricks here and still maintain all the data. It could have been implemented the other way, by the way. It's just that initially they were both implemented as replicated, and we found that we could get more space for logs if we used the other mode. So we did that. And this is let's see. And we're going to have 15 minutes for questions. This is good. Okay, so Grafana KPI visualization. So this is the last section. So this is an example. So the Grafana implementation is not part of the Volta implementation. We implemented this as an example to show how you could pull KPIs or events off Kafka and graph them successfully using Grafana. Okay. So there's multiple containers involved. Grafana is the visualization container. It contains the Carbon daemon, Graphite, and Grafana. So all 3 of those are inside the one container. Shovel, which is an interesting name for the process that shovels the data off of Kafka and sends it to the Grafana container. -D. So -D is responsible for a couple of things. One is setting up the data source that Grafana will be using, and then also creating dashboards for the devices. And finally, Kafka is a source of KPIs on the volta.kpis topic. So -D maintains a list of devices, and it maintains a list of dashboards. as a new device, so it's very important to understand that -D doesn't do anything but monitor Kafka. So if you add a new device to the system and it's not publishing KPIs, you won't see a dashboard on Grafana. It'll never appear until that device publishes its first KPI. And then the dashboard gets created in Grafana, and from then on, you will see any KPIs a device publishes be displayed. If -D crashes, when it comes back up again, the first thing it'll do is read all the dashboards that Grafana has and hold on to them. And as it's getting KPIs, it checks to make sure that that dashboard hasn't already been created. If it has, it doesn't bother doing anything. If a new KPI gets published for a device, then it will create a new dashboard. -D will never delete anything yet, at least not now, mostly because if it could have been a manually created dashboard, and if it comes up and goes, oh, well, I should have no dashboards, and deletes them all, then it might make someone angry who spent days creating a nice dashboard that's not the same. There's a dashboard template in -D as well, so that can be changed. It's actually a Python dashboard definition. And finally, this whole system communicates through VoltaNet. So very simply put, you've got Volta publishing KPIs to Kafka. Shovel is reading KPIs from Kafka and pushing them to Grafana, which are being basically put in the whatever the Carbon daemon is using as a database. And then -D is also monitoring Kafka, and as it gets KPIs, it determines whether or not it needs to create a new dashboard in Grafana. And it also reads, as I said earlier, the dashboards, and it does create the data source because Grafana needs a data source to run, and the Grafana container has no persistence. So when it first comes up, it has no data source. So what -D will do is it'll check if the data source is there. If it's not, it creates it. And that's it. Wow, that was quick for 30 charts. So we have 11 minutes left for questions if anybody has any. Yes? Today, there's a finite list of KPIs, and they are counters for different packet sizes, is what we settled on for the initial implementation. So packet sizes, say, of 64 bytes, and then of 64 to 128, 128 to 256. So those counters are published, and then we're using Grafana's capability to convert multiple readings into a packet per second view on the dashboard. Oh, I guess I'm crystal clear. This is great.
What you have time for the flows you want to describe? Actually, so we discussed this, right? So with the flows right now doesn't
have. It's only for edge core that we have to run a single instance stack, top to bottom. Onos will actually run and start in HA mode when we're using other PON devices. But today, because of the nature of the adapter for the edge core device where it needs to call back, you can't have multiple IP addresses for the callback. And so you end up with a situation where you have to have a single instance that can be called back.
HA running the 2n+1 mode?
Yeah, yeah, we can start in 2n+1. And in fact, we were doing that during the POCs.
So you've actually used Volta and HA mode talking to
Onos and HA mode, yeah.
For other...
Yeah, for other devices, but not for the edge core device, because adapter is so new on edge core, right? Once that evolves, we'll have, or once we evolve. So
can you explain that callback? What was the problem?
Because gRPC is a bidirectional mechanism. So the adapter establishes a call to the edge core device southbound, and then informs it of an IP address for it to call back, so that you can send gRPC requests in both directions.
Between Volta and the edge core device,
yes.
Does that have to do with Onos then?
No, nothing, but we're starting everything in single. So we have to start Volta in single instance. So we're just running Onos in single instance as well, because why have the redundant? Well, you could have the redundancy. If Onos crashed a lot, it would be useful, but it didn't do a lot of crashing while we were doing the trial. So we just ran everything in single instance. But you're right, Onos could be run in clustered mode. But since we were running everything on one server, you know, it was easier to do it that way.
Sergio can add to that, just the recent commits over, I think, the weekend and Friday should have put the.
Solve that problem?
Should have put the capability to solve that.
Okay, good.
Looks like it, so now it was demonstrated to come up with a swarm.
Okay.
Be able to reconcile, so. it
Perfect.
has to further be tested.
And this is this is straight from the horse's mouth. He's developing the adapter, so so you got to believe him, not me. So the other thing I wanted to quickly say about adapters is that the intent is to pull all the adapters out into their own Docker containers, so they are disaggregated from Volta. There's a few other things we want to disaggregate from Volta as part of release 2. The coordinator will probably be disaggregated from Volta, and the dispatcher will no longer be. Well, the dispatcher will be required. It'll be disaggregated, but not for reads, only for writes into Volta, because there's another part of the HA strategy, which is to have read-only containers, which means that it doesn't matter if one crashes or another one crashes. You can round robin to any of them to get the information because they all have access to etcd. And then there'll be write containers that are paired active standby and with state identical in both, which means that if one crashes, the other one it's the old telephony thing, right? Where you can just do a SWACT over to the standby card, and lo and behold, your system is back up and running. It's the same kind of scenario. So you'd have 6 read-write cores running and 3 read-only cores running in a 3-server configuration, and that will give us sub-second, actually sub-millisecond switch times theoretically. That's just a preview of what we're, and Kubernetes is in for release 2 as well. So we're replacing pure Docker Swarm with Kubernetes implementation for container management.
Possibly will be 1.3.
Possibly in 1.3. Well, Kubernetes working, right? In our little, what we call the VOLTHA environment, the Volta HA environment, VOLTHA. So we've already got it running in there. We haven't replaced.
Given that it's already a lot of maybe different versions of different software.
So the idea, which there's a Jira for that, for locking down the versions, which is sitting on my plate, unfortunately. So
it was like a few weeks ago.
I never got that submitted on Hawaii time a few weeks ago. You know why? You know why? It's because the flight I took home was supposed to have go internet, and it wasn't working, so I couldn't do anything on the way home. And so anyway, we're going to lock down all the versions of these things, and Docker actually offers a rolling upgrade capability, and we tested it actually during POC 3. So if in the compose file you change the version of the container you're running, and you basically do a Docker stack deploy of that compose file, what ends up happening is that Docker will notice that the version you've listed in the compose file is different from the version that's running. And so what it'll do is it'll basically bring one container down and bring up the new version, wait for it to come up and make sure it's successful. If that succeeds, then it'll go and bring down the next container and bring it up. So upgrades are not that complex. And as long as you understand that upgrading a specific container with the rest of the lineup remaining where it is will work, you can apply that. And there may be a staged mechanism where you have to upgrade them in a certain order. So let's say Kafka needs to go first before the Volta Core does. You can make sure that whatever upgrade mechanism you're using targets Kafka first. When that's successful, then it targets Volta Core. So yes, there's a lot of containers, but we will always define a lineup at some point. Like when we cut a release, we'll define a lineup at specific versions and an order in which you need to upgrade the containers for the entire whole to succeed. Because we may be changing, etcd or console keys, right? And so you can upgrade Envoi D before you, or you can upgrade the etcd cluster. You probably have to upgrade them both at the same time. So you have to launch both compose files together, and then eventually they'll all come up and reconnect. So, and we need to version some of our APIs. Today, there's no API versioning, which can cause a lot of issues as well. So you never know if you're talking to the right version of your southbound or your northbound. Did that sort of answer your questions,
Yes.
Rob? Okay. 5 more minutes.
So, there's so many open source software selected to be part of this framework. How was the decision made, for example, console was big to do this, and then now console is flaky?
Okay, so the console was selected for a very specific reason. It supported DNS services. It supported a key value store, and there were other applications that would interact with console, like Registry, which would automatically register a container into console when it came up. We don't use those services anymore because Swarm has them all. So the decision was based on using vanilla Docker, not Swarm, not Docker Swarm. And we needed a DNS service. We needed a way of registering the containers as they came up and their IP addresses and all that. And it became a very simple decision to look at the market and say, this is the only game out there, the only game in town right now. And running it as a single instance, it was robust as all hell. The only time console gets flaky is when you're trying to run it in clustered mode, right? So as long as, you remember, POC1 was a single instance of all these containers. It was robust. It worked well. The DNS services from console worked the way they were supposed to. Everything was nice. It's only when we started to run console, trying to run console in HA, and then we'd bring it down, and then we'd bring it back up, and leadership election was just failing all over the place, and then we're getting RPC errors, all sorts of stuff. So it took a lot of tweaking on the options and massaging it, and we finally got to a point where it was fairly robust. You could pull a plug on a server and then plug it and then reboot it, and it would come back up, and then Swarm would reestablish its connectivity, and console would re-elect a master, and things would work. But it was a lot of trial and error, and luckily we had the tools to bring down and bring up Volta and kill VMs and recreate VMs. We were doing all this on VMs, because it was the only way. So that's why we ended up with the flaky key value store, because it wasn't thoroughly tested, right? When you make a decision on what technology you're going to use from the open source community, it's very difficult to go and test it thoroughly to make sure it works. It's only through, okay, let's extend it and use it in a new type of configuration that you find out, maybe this wasn't the best decision to begin with. The other thing is that a lot of the decisions that we made early on were based on a book called DevOps 2.0, which is basically a microservice architecture book that walks you through all these different things that you can do, continuous builds, continuous upgrades, right? Continuous testing, all this other wonderful stuff. And console was ranted and raved about there. So we said, okay, well, we'll just use it. There's actually DevOps 2.1 now if you want to read the latest version of that book, Sean, because I see you making a note. So
No, I'm going to put it on the wiki page of Volta.
So if anybody wants to read a really great book on DevOps, this DevOps 2.0 or DevOps 2.1, I think the latest version is a pretty good book. But it expects you to sit in front of a terminal with Docker and actually do examples live. It's not something you can just read on a plane, because you'll quickly lose sight of the examples and what they're trying to achieve. Any other questions? We got 30 seconds.
Yeah, I got a 30-second question.
Okay.
What do you expect is going to be the extent of adapter changes when they containerize? What we have is the adapters you run as part of the V Core, right?
Yep.
So when these become containerized,
The intent
what
is
has to be different?
not to change the iAdapter interface. So within the vCore, you'll still make calls to the iAdapter interfaces. And what we're going to do is create for gRPC south and northbound to the container, and the container and an equivalent shim for the container to communicate with the core. And that should solve 90% of the cases. If the adapters using other Volta, going straight to KV store, for example, which if that's happening, then we're going to need to make we're going to either need to revisit how the adapters are implemented or make the changes required to that interface to make sure that the adapters can get access to what they need in the core.
Good.
Okay, let's thank the
Okay.
speaker.
Thanks, Sergio.
Sergio.